Hello, in this video we're going to be talking about AP Chemistry's topic 7.4, calculating the equilibrium constant. So we've talked about the equilibrium constant and how it establishes whether a reaction is reactant favored or product favored, and quantitatively allows us to figure out how much product is produced in a reaction and how much reactant remains in a reaction. So we are going to practice calculating an equilibrium constant because equilibrium constants always have to be determined experimentally. In other words, you have to do an experiment in order to determine equilibrium constant. Scientists don't just make equilibrium constants up. Reactions occur in a certain way, and the equilibrium constant comes from how those reactions actually occur. Now, just a reminder, equilibrium constants are temperature dependent. And so if you change the temperature of a reaction, then the equilibrium constant will also change. So we are going to be practicing the calculating of an equilibrium constant with this problem that I've given you here on the screen based on this reaction between nitrogen monoxide and chlorine. Let's just write down what the equilibrium expression for this particular reaction is going to be. So the equilibrium constant in terms of concentration is going to be calculated by taking the concentration of the product and raising it to its coefficient power and divide by the two reactants. Nitrogen monoxide's concentration raised to its coefficient power times the concentration of chlorine raised to its coefficient power, which is a 1. So our equilibrium constant is the ratio between the products and the reactants. We could also do the equilibrium constant for pressure because all of these substances are gases, and so we could calculate the constant for pressure, but we are going to calculate the equilibrium constant Kc for the reaction in this problem, so we're just going to write the equilibrium constant in concentrations. So how are we going to solve this problem? Well, notice that everything is in concentrations in this problem, and if you look at our problem, it says that we have 6 moles of NO and 6 moles of Cl2. Those aren't concentrations, but it does tell us what the size of the container is, 3 liters. And if you recall, the way you calculate molarity is equal to the moles of the solute, the moles of the substance being dissolved, divided by the liters of the solution. Now, in this case, we just have this gas in a 3-liter container, so it's the moles divided by the volume of the container. So the concentration of NO is going to be the moles, 6.0 moles, divided by the volume of the container, which is 3 liters. And 6 divided by 3, of course, is 2.0 molar. So the concentration of NO is 2.0 molar. And this is our initial concentration before the reaction even takes place. So I'm going to put an I there. The concentration of Cl2 is going to be exactly the same because we have 6 moles of Cl2 and we also have the same container, 3-liter container. Then an experiment was done with these two. They reacted with one another, and after they reacted, 0.1 moles of gaseous NO remains in the container at the end. What is the value of the equilibrium constant? So at the end of this reaction, we have NO still in the container, but now there's only 0.1 moles. So 0.10 moles divided by the 3-liter container. And this gives us a final concentration of 0.0333 molar. Okay, so now we know all the concentrations that are given in the problem. How are we going to solve this problem? Well, we need to figure out at equilibrium how much NaCl is present, how much NO is present, and how much Cl2 is present in concentration. We know the NO, but we don't know the other two. So in order to solve this problem, we're going to have to use stoichiometry, and we're going to use it in a convenient way, a Rice table, which we've talked about before, but let's go through it again. R stands for the reaction that's taking place. I stands for the initial concentrations. C stands for the change in concentrations. And E stands for the equilibrium concentrations. So our reaction, I'm just going to rewrite the reaction here. 2 NOs plus Cl2 forms an equilibrium with NOCl. So our initial concentrations, we know the initial concentrations of everything in this problem because we calculated them right over here. The initial concentration of NO is 2.0 molar. the initial concentration of Cl2 is 2.0 molar. And what's the initial concentration of the NaCl? Hopefully you said 0, because there is none present in the container initially. Change. So how much did these substances change? Well, we don't have direct information about that, so I'm not going to fill in anything quite yet for the change. But we do know something about the equilibrium concentrations. We know the equilibrium concentration of the NO, because at the end it says there's 0.1 moles in the 3-liter container. So our equilibrium concentration of NO is 0.0333 molar. So what does that mean about the other substances? Well, we're going to use stoichiometry in order to do that. So in order for us to end up with 0.033 molar of the NO, we had to lose some of the initial concentration. And how much did we lose? Well, we lost whatever 2 minus 0.0333 molar is. And that, if you do the calculation, is 1.9667 molar. We lost 1.9667 moles per liter of the NO in this reaction. Now let's look at the stoichiometry, because the stoichiometry is going to tell us how much of the Cl we lost and how much of the NaCl we gained. So for every 2 NOs, we're going to lose 1 Cl2. It's a 2-to-1 ratio. So this is twice as much of the Cl2 that we lost. So we're going to divide this number by 2 to figure out how much what molarity of Cl2 we lost. And if you divide that by 2, you get 0.98335 molar. So that's the amount of Cl2 that we lost. So if we do the subtraction, 2 minus 0.98335, that gives us 1.01665 molar at equilibrium. So now we know how much Cl2 is present at equilibrium, or the concentration at equilibrium. We just calculated. How did we do that? Using stoichiometry. Twice as much NO was lost as Cl2. Now if we look at the NaCl, we're only going to gain NaCl because we initially had 0, so we can't lose any. We must gain it. And how much are we going to gain? Well, 2 and 2 were the same coefficient. So however much we lost of NO, we're going to gain of NaCl. So the amount we lost right here, the molarity we lost right here, that's the same molarity we're going to gain over here. So our equilibrium concentration is going to be 0 plus 1.9667 molar. So now we know the equilibrium concentrations of all substances in this reaction. So now it's going to be very easy to calculate our equilibrium constant, because we just need to plug in all the equilibrium constants into the equilibrium expression. So let's go ahead and do that. Our NaCl concentration is 1.9667 molar, and we're going to square that because of the coefficient in the problem. We're going to divide that by the NO concentration, 0.0333 molar, raised to the second power because that's its coefficient. And Cl is 1.01665 molar. And that one's just to the 1 power because its coefficient is 1. So now all we have to do is do the math. And if you do that on your calculator, you'll get 3.4 times 10 to the third for the equilibrium constant. Notice I'm not putting a unit here because there are no units in equilibrium constants. No matter what units are used in the calculation, we don't put any units on the equilibrium constant. So the equilibrium constant is 3.4 times 10 to the third, which is 3,400. That's a very large, well, that's not very large, but that's a large equilibrium constant, meaning that this reaction is very product favored. We produce much more products than reactants in this equilibrium. And if you look, we actually did that. We made a lot of product and lost a lot of reactants. So this is a product favored reaction. So that's our equilibrium constant. These always have to be experimentally determined. You always have to do an experiment in order to calculate the equilibrium constant. And this is just one example of how to go about doing this calculation. If you need some more problems or you need some more help with this, please talk to me. I'll be happy to help you. And good luck.